So before we discuss more about enzymes, let's first differentiate uh, what allows for a reaction to proceed, right? So let's consider this question first. So a chicken breast is composed of about 25% protein, okay? Adding a chicken breast to a glass of water should cause it to hydrolyze all the proteins and dissolve. Why doesn't this happen? So the premise for this is, if you remember this from back in chapter 4, we talked about condensation of two amino acids forms a peptide bond. Okay, so remember this is amino acid 1, this is amino acid 2. You lose a molecule of water and you form the peptide bond. And so remember, the delta G for this is positive, so this is energetically unfavorable. So the reverse reaction, where the peptide bond is broken, okay, is called hydrolysis. So the reverse of condensation is hydrolysis, as shown here. And hydrolysis will break the peptide bond. Again, this is just the reverse of condensation. Okay, so change the reactants and the products shown in the scheme. And then you also would flip the sign of the delta G value for hydrolysis compared to condensation. And so hydrolysis, remember, then is going to be energetically favorable because the delta G, the standard free energy change, will be negative 15.0 kilojoules per mole, which means it will be product favored. Okay, so going back to this question then, so let's consider this. If we think about this, this is the delta G is going to be negative, and so this will be thermodynamically favorable, but we don't have a problem. For instance, if we take a piece of chicken and throw it in a glass of water, it's just going to look at us for a while, right? It doesn't start to hydrolyze on us. Okay, why is that? And so the answer is that it's not all about thermodynamic favorability. So even though this should be product favored, there's also a kinetic barrier involved. Okay, so the rate, in other words, the rate of the reaction, which is dictated by kinetics and what we call a kinetic barrier, has a say in how likely this reaction is going to occur, at least how fast this reaction is going to occur. So even though it's thermodynamically favorable, the kinetics are such that the half-life for peptide bond cleavage by hydrolysis is 350 to 600 years. Okay, so even though we have this thermodynamically favorable reaction, it's really, really, really slow. Okay, and so we don't see that within, a reasonable time of observation and experiment. So it would, the chicken, would be gone for many other reasons, mostly, for instance, microbial degradation or rotting, right, before it degrades because of hydrolysis. All right. So to look at this, right, to understand this concept of thermodynamics versus kinetics, we need to review reaction coordinates. So if you remember these, you probably have seen these in general chemistry and organic chemistry. And so they're typically drawn as a curve where there are, for instance, levels on the reactant side and the product side. So if we're looking at a reaction where the reactant is S and it's converted to P, all right, and it's in equilibrium, you might see a level for S, a level for P, and in the middle, a giant hill. And that you've probably seen this a couple times, all right? So these aren't typically drawn with axes, but we'll define what the axes are. So first of all, the y-axis is a free energy change. Okay, sometimes this is also expressed as an enthalpy change, but for the most part, we'll be looking at free energy changes. So delta G. Okay, so the higher up on the graph, the higher the delta G, the energy is. Okay, and then the implied x-axis is reaction progression. And so there are a lot of different ways to express this quantitatively, but for your purposes, what you'll just consider is, okay, as S is converted to P. Okay, just think of a progression of the reaction from S to P in this case. All right, so there are a few features that are really important. Okay, so these dashed lines, these dashed black traces, are just projecting the energy of, for instance, this top one is the energy of the free energy of just substrate or the reactant S. Okay, just across the graph here. Okay, so that we can compare the energy of S and the energy of P. All right. So the distance between the energy of S and the energy P, that's delta G. Okay, so it's the change in free energy for converting S to P. Okay, and this is what we can do to, for instance, figure out an equilibrium constant. Right. Now in the middle, right, the energy from S, and in this case, to this first hill, that's called an activation energy. Right? And so what that is that tells us the energy it takes in order to overcome this kinetic barrier, and then once if there's enough energy supply to overcome this kinetic barrier, then that can proceed to product. All right. So it's not just about the energetics, right? The thermodynamic, about the thermodynamics, which is measured by delta G. It's also about the height of the activation energy. And so to give names to these features, so S and P, so these lie in what are called potential wells. Okay, so you can just think of this as this local minimum where S is, and this local minimum where P is. You can think of as a well, such as like a water well, right? So, but they're just local minima in the reaction coordinate. And then where there are local maxima, right, this is called a transition state, all right? And so the transition state energy dictates how fast. So transition state energy, as expressed by the activation energy, dictates how fast a reaction can go. So the higher the activation energy is, in general, the slower the reaction will be, because it takes more energy to overcome that transition state energy or the activation energy. Okay, versus the lower this activation energy is, the faster the reaction goes. Okay, and so the thermodynamics, another way to say thermodynamics, or something being thermodynamically favorable, is the driving force, right? So if there's a negative delta G, then there's a thermodynamic favorability towards products, but there still has to be a consideration of the rate, as we see, as we discussed, for hydrolysis of chicken breast.